Good day everyone, this is going to be the first problem of today's presentation. So, four concentric circles with the radii in the ratio 1, 2, 3, and 4 are drawn with the corresponding colors pink, orange, yellow, and blue. If 4 points are randomly placed inside the largest circle, what is the probability that each colored area has 1 point? If a point randomly placed inside the largest circle, what is the probability of landing on either orange or blue areas? How do you think we should go about solving this problem? For me, I would personally prefer to visualize the problem to get a better idea of what we're dealing with. Since the circles are concentric, that basically means that they share the same center point. Here you can see the four circles with their respective radii, and we're going to assign their respective colors. So here you can see the circle with radius 1, 2, 3, and 4. So how are we going to be getting the probabilities for each segment? We will be calculating for the areas of each circle using the formula of the area of a circle, which is pi r squared, since we are given the values of the radius. Now we are going to make the figure concentric by stacking the circles on top of each other. As you can see, the shape mostly resembles like a dartboard, and in this case we'll only be counting points, or like the darts in the problem, that are within the figure. So our max area or total area for this problem will be the area of the biggest circle, which happens to be the circle with a radius of 4. And using the formula, we get that this circle has an area of pi over 60. So as you can see here in this list, we're just calculating all the different areas of the segment. So here in the blue area, we can see that is the area of the biggest circle, which is A4 minus A3, which is the yellow circle. And we're going to be plugging in the areas, and we're going to be subtracting values. So that's going to be 16 pi minus 9 pi, which will be 7 pi. And here for the area of the yellow circle, it's going to be A3 minus A2, orange circle A2 minus A1, and finally for the pink circle, or the pink area, it's just going to be the area for that circle alone, since it is the smallest circle. And to calculate the probability, we have the formula, the area of the segment over the total area. So that's going to be the area we just calculated over the total area, which we know is 16 pi, like we mentioned earlier. So here you're just going to see me divide all these values, all the new values of the areas of the segments, by the total area. So that's going to be 7 pi over 16. That's going to be 5 pi over 16 pi, and 3 pi over 16 pi, and 1 pi over 16 pi. So we're going to cancel out the values of pi, and that's going to give us the percentages for the corresponding, or the percentages of the corresponding probabilities of the dot being in that segment. So going back to the problem, it's actually asking us, if 4 points are randomly placed inside the largest circle, what is the probability that each colored area has 1 point? So that basically means that all the points have to be on different areas of the circle at the same time. So how we're going to be solving for that is we're going to be multiplying all the different probabilities that we just computed for together, since we're looking for the simultaneous probability of all these points.
So hello, today I'll be answering problem number 2 for our discrete probability problems. And the problem is as follows. Each batch of fresh orange juice contains either 1000 liters of orange juice, which is 15% solids by volume, or 500 liters of juice, which is 25% solids by volume. And if 4 random batches are mixed, what is the probability that the mixture is at least 18% solids by volume and B less than 25% solids by volume? So the first thing we need to determine is the mix of solutions that will satisfy this condition here, which is at least 18% solids by volume. So in order to do that, we need to first get all the different possibilities of mixing the orange juice batch. And we said here that we were going to choose 4 random batches, and they were going to be mixed, and each of the mixed batches of orange juice will have an output different output with a different concentration. So basically, what do I mean by that? So let's write here, mix of solutions. So we were going to pick 4 different batches. So if the first one was 25%, and the next one was 25%, and the next one was 25%, and lastly, we get another 25% from the batch. The output concentration would be equal to, of course, just 25% total concentration. Okay, now, but what if we pick 15% for the first one, and then the rest were 25%, 25%, and 25%. The output total concentration would be the total solids divided by the total volume. So we said that in the 15% solids by volume, we had 1,000 liters of juice. So that's 1,000 liters of total volume, and 15% of 1,000 is basically 0.15 multiplied by 1,000, which is 150. So that is your concentration as a fraction. Now we're going to add 25% to this mix. So basically that's 25% solids divided by the total volume, which we said was 500. This is going to equal to, the 25% of the 500 solids will be equal to 125. 125 of those will be solids. And what we're basically going to do is basically represent the final concentration as the total solids divided by the total volume. So to add up all the concentrations, we said that the 50% had a 150 liters of solids, so that's 150, plus the 25% we said had 125 solids, liters of solids, and then 125 again plus 125 over the total volume of this entire mix, which was 1,000 from the 15%, and 500 plus 500 plus 500. So our final concentration would be 21%. So we write that here, 21% final concentration. So we basically have to do that for all the different mixtures of the batch. So 15%, 15%, and then 25%, 25%. If we use the same steps for this one, we would get 18.333%. And then if we picked out 15%, 15%, 15%, we would get final concentration of 16.429%. And then if we were to pick out 15% for all four, then we would get obviously 15% for our final concentration. So if we model this as a binomial distribution where we let the random variable x be the number of 15% orange juice that we select number, forgot the right number there, selected, then we would have n is equal to 4 because we picked out 4, and then p would be equal to 0.5 because we only had two choices for the orange juice, either the 15% or the 25%. And our q would be 1 minus 0.5, which is just 0.5. And so our probability function would be ncx and then p raised to x and then q raised to n minus x. Should be n is equal to 4, and we have x, and p is 0.5, x, and then q raised to n, 0.5 n minus x. So this is our probability function. And now we can solve the problem. So for part A, we said that at least 18% solids by volume. So which of these concentrations will produce at least 18% solids by volume? So that would actually be this here, here, and here. So these three right here. If we get no 15%, if you get one 15%, or if you get two 15%. So we can write that as so instead of actually getting the probability of these three, we can just do 1 minus the probability of these three because it's faster, because we just have to calculate two. So in order to do that, we do 1 minus the probability that x is equal to 3 plus the probability of x equal to 4. And if we write that out, we get 4, 3, and then 0.5 multiplied by n is equal to 3. N minus 1 is 1 plus 4, 3, 4, and then 0.5 raised to 4, 0.5 raised to 0, which will equal to 0.25 plus what is this? This is 0.0625. Now we add those together, we get 0.25 plus 0.0625. We get 0.3125. I know we said 1 minus that. We get 1 minus 0.3125. we get the final answer of 0.6875. So this is our final answer right here. So now the next problem is B, which is less than 25% solids by volume. So the only time we get less than 25% solids by volume is we basically don't get all 25% concentration. So if we were to write that down, we get an expression one minus the probability of x being 0, where we said x was the number of 15%, b the number of 50% orange juice selected. So this will simply be 1 minus 4, x here is 0, so that is 0.5, 0.5 raised to 4. And this will equal to 1 minus 0.0625, which will be 0.937. Oops. 0.9375, and that is your answer for D.
Alright, so we're now moving on to the problems involving continuous probability distribution. Here's our third problem. I'll read it first. A feed gas is treated with water to remove impurities in the gas, which composes 1% by mass of the feed gas. We'll call feed gas Fg and water as W. The rate at which the feed gas enters the treatment machine starts at 20 kilograms per hour and gradually increases such that the rate is doubled every 24 hours. If the likelihood of a malfunction in the machine is a random variable with continuous uniform distribution over 7 days, and it reverts the feed gas rate to 20 kilograms per hour, what is the probability that the treated gas, or TG, is at least 1,000 kilograms since the last malfunction? Okay, so the problem is quite wordy. So the first step in solving is to understand the process that it describes. We can try drawing the process flow diagram to make the given more easily visualizable, I guess. Although we can still proceed with the solution as long as we can track of the given. Anyway, we'll go with the solution with drawings. It was said that there is a machine that treats gas. That's a treatment machine. Usually it's absorption column. Anyway, the feed gas or an entering gas is there. It starts at 20 kilograms per hour and it has 1% impurities, meaning 99% of the feed gas is safe gas, or the gas that will eventually come out of the treated gas. there is an additional information saying that the feed gas doubles every 24 hours. The rate of the feed gas doubles every 24 hours. The feed gas is treated with water, and of course, it will produce two streams. The treated gas, which is purely the safe gas coming from the feed gas, and the wastewater, which contains the water and the impurities from the feed gas. Okay, we will be using this process flow diagram to solve the question. We know that the feed gas starts at 20 kilograms per hour and it doubles every 24 hours. We can create a function out of that. This one, the rate of the feed gas is equal to 20 times 2 raised to x over 24, where x is in hours. As we can see, after 24 hours, it will be, the feed gas rate will be 20 times 2 raised to 24 over 24, or 40 kilograms per hour. After 48 hours, it will be 80 kilograms per hour. So this function satisfies the condition that the feed gas doubles rate every 24 hours. Next, to get a function that will calculate the feed gas given an amount of time, we can integrate the function of the feed gas rate, the rate function. If we integrate that with respect to time, so we'll have the integral of 20 times 2 raised to x over 24, we'll get the total kilograms of feed gas fed. So now we have a function in time. We now have a function in time of the total feed gas, but the problem asks for, hold on. And the problem asks for the probability of the treated gas being at least 1,000 kilograms, since the last mole function. So our given here is the treated gas, not the feed gas. For that, we have to use the relationship between the feed gas and the treated gas. 99% of the feed gas, as shown here, is safe gas, and that safe gas is the entirety of the treated gas. So for that, we can use 1,000 kilograms of treated gas divided by 0.99, and we'll get the total feed gas to be 1,010.1010 kilograms. So by the time that we have treated 1,000 kilograms of treated gas, the feed gas should have been 1,010.1010 kilograms. So we now have a total of 1,010.1010 kilograms feed gas, and we have a function that describes the feed gas in terms of time, with a variable of time. With this, we can get, we can solve for the time that it takes to produce 1,000 kilograms of treated gas, and that is this equation. 1,010.1010 is equal to the integral from 0 to a being the unknown, of 20 times 2 raised to x over 24 dx. And further solving this, we'll get this equation. I used a calculator here, but we can probably still solve this manually using the laws of integration or the techniques of integration. Anyway, substituting the limits of integration, a and 0, we'll get this. I've also divided the factors of the right hand side in here. So anyway, simplifying this, we'll get a equals 24 times log to the base 2 of 1,010.1010, natural log of 2 over 15 times 2 raised to 5 plus 1. And we can calculate this. By the way, if your calculator is old like mine, you can probably use the change of base formula. This, when log base 2 of something, that's also equal to log of something divided by log of 2. Ayan lang. So A is approximately 31.1487 hours. That's also 1.2979 days. And we can use this value later. The interpretation for this is that the feed gas, which doubles every 24 hours, doubles rate every 24 hours, will take a total of 31.1487 hours to produce 1,000 kilograms of treated gas. And that's what we need in the problem. So we can start solving for the probability now that we will produce more than, or at least 1,000 kilograms of treated gas. And for that, we can create a function, a probability density function, wherein this is in days, by the way. So I use the days here, wherein from day 0 to day 7, from day 1 to day 7, we'll get a total of probability of 1 as given in the problem. Ayan. The likelihood of a malfunction is a random variable with continuous uniform distribution over 7 days. So the process will malfunction once in 7 days. And we don't know when within the 7-day period. So we can plot that graph as a continuous uniform distribution. So that's gonna be a horizontal line with equal likelihood, which is 1 over 7. The total area for this should be equal to 1. And as we see, 1 over 7 times 7 is equal to 1. Anyway, we will be getting the probability of the process being operating from 1.2979 days onwards. So that's from 1.2979 to 7. We can integrate the function f of x, which is 1 over 7, from 1.2979 to 7. Or we can just calculate the area of the shaded region, the rectangle. Here it is. I use the area of the rectangle. This is length 7 minus 1.2979 times width 1 over 7. And we'll get the probability of treated gas being greater than or equal to 1,000 kilograms to be 0.8146. Ayan. Okay, so that's it for problem number 3. We'll go to the next problem, which is also a continuous probability distribution. This problem is a bit more straightforward. I'll be reading this first. An average of 200 machines in a gas treatment plant malfunctions every day. If the number of malfunctions follow a Poisson distribution, A, what is the probability that there are at most 180 malfunctions in a day? B, how long is the expected time to reach 1,000 malfunctions? And C, what is the probability that there is at least one malfunction in 20 days? All right, so we have lambda equals 200 and we'll have to approximate the probability of x being less than or equal to 180. I said that there should be at most 180 malfunctions in a day. We'll use the approximation using the normal distribution in here. And we can write that as the probability of x being less than or equal to 180 if approximately the probability of z being less than or equal 180 minus 0.5, 180.5 minus 200 all over the square root of 200. And that is approximately negative 1.3789. We'll use the C table to compute for this value and we'll get 0.0840. That's the final answer for the first question. So we have an around 8.40% chance of having less than 180 malfunction, less than or equal to 180 malfunction. For the second question, how long is the expected time to reach 1,000 malfunctions? So that's a bit easier. 1,000 malfunctions divided by an average of 200 malfunctions per day. So the expected time should be 5 days. The last question is that what is the chance of the probability of at least one malfunction in 20 days? So just thinking about the given, it's almost certain that we'll have one malfunction, right? So the answer should be 1. Kasi kung 200 nga naman yung average in a day, what more if we have 20 days, no? Tapos one malfunction lang ang hinihingi. Anyway, we can use the formula for the Poisson distribution in here where lambda is 20 times 200 or 4,000. And then we'll be calculating the probability of x being greater than or equal to 1, at least 1 kasi. And that should be equal to 1 minus the p of x less than 1, or 1 minus the p of x equals 0. So calculating the p of x less than 1, that should be e raised to negative 4,000 times 1,000 raised to 0 all over 0 factorial, or e raised to negative 4,000, which is approximately 0 since this is a very, very small number. With that, we'll get the approximation that we initially got, which is the p of x being greater than or equal to 1 is approximately 1. All right, so that's the last part of the continuous probability distribution.
Hello, so for problem 5, a random lattice point, which we define as a point with integer coordinates, is chosen in a Cartesian plane such that both the abscissa and the ordinate range from -5 to 5. If each possible point has an equal probability of being chosen, we need to A, find the probability that the point is outside of the circle x squared plus y squared equals 25, and B, find the marginal probability P of y equals 0. Right, so the way we can do this is through graphing. So we do solution by graphing. So we can plot the circle and the lattice points in a graph or a quadrant so that we could save space. And we can also count the points outside the circle, which are 40 points. And then dividing all those 40 points dividing the points outside the circle with the total points, which is 121, we get 40 over 121. And then the points where y equals 0, and so we need to find the points where y equals 0, and it's seen here, which is boxed in green. So to simplify that, P y equals 0 equals 11 over 121, and if we simplify that, that becomes 1 over 11.